Okay, so and Shing Yan will tell us about large U1 charges with flux breaking and 4D F theory models, please.
Okay, first of all, so thank you for the organizers for inviting me for give a talk here. It's my first time to give a talk in the string field seminar, so I'm very happy to do that. So today I'm going to tell you something about obtaining very large U1 charges from the flux breaking in 4D F3 models. This is based on a paper that is out in November last year, working with my supervisor, Wati Taylor. And first of all, let me tell you some motivation of why we are interested in this problem. Oops, sorry. Yeah. So the motivation is, well, it's a long-standing Swarm question. We all know that string theory impose many tight constraints on what kind of low energy we can have, what kind of theory that we can have in low energy. And a very concrete Swarm question is the following. So what kind of matter can be realized in string commodifications? Or to be more precise, given that, let's say we have a gauge theory in the low energy, and then what will be the gauge charges that the matter occupied that can be realized in string commodifications? This is, of course, a very long-standing problem. And in particular, if we include all the physical states in the theory, then there's already a well-known completeness hypothesis that said that upon gauge charge quantization, all gauge charges should be realized as some physical states in the theory. So that's kind of already trivial to us. But if we try to restrict ourselves to look at some massless or light fields, or in our context, it will be, well, maybe it's a chiral fields or it's a vector-like fields. So the main point is it's fields with not very large mass, then the problem becomes much more non-trivial. So because we believe, let's say the landscape is finite, then we would expect there is some upper bounds for the charge that can be realized. But it is totally unclear what the bound would be. So nowadays, for now, we have very little idea on that problem. And in particular, we would like to ask how large the U1 charges can be realized. So this is a particularly hard problem for the following reason. But before talking that, I want to fix the normalization that we use, because we can always rescale our U1 charges. So what kind of values are we talking about? So our convention is that we normalize the charge such that all charges are integers, with the greatest common divisor being 1. And U1 is particularly interesting for the following reason. So first of all, when we're looking at string theory solutions for a problem like this, it's kind of natural to look at F-theory compactifications, because F-theory currently gives us the most, the largest set of string compactifications in string theory. And most work about U1 in F-theory is done in 6D. So in 6D, U1s are very hard to construct, because let's say if I want to construct a nonabelian group in an F3 model, what I need to do is to specify the local geometries, or in the usual string theory language, I need to specify the brain stacks supporting the nonabelian group factors. But for the U1, it's a completely different story. We need to look at the whole global geometry in the internal manifold, and to be precise, it's called the model wheel group of rational sections of elliptic vibrations for the U1. So I don't want to dig into what that thing is, because it's not our main point. But the thing is, it relies on the global geometry and it's very hard to construct. And of course, we would expect the possible charges from there is very limited. And in fact, in literature, the explicit constructions are only up to Q smaller or equal to 6. So that's a pretty small number. But on the other hand, if we don't look at explicit construction, let's say we look at hex mechanism in low energy that correspond to geometric deformation in F theory, then there's an implicit argument that tells you Q may be as large as 21, but those are not explicit string constructions. And if we just look at, let's say, anomaly cancellation in low energy, then there will be infinite, of course, infinite possibilities of the charge Q. And that infinite possibilities, so infinite part of them will belong to the Swarm. So in short, we have very little understood for Q greater than 6. But all the analysis above are did in 4D, did in 6D. So how about 4D? So 4D story is very different because now we can include flux background, and it's known that the flux can break non-abelian gauge groups down to some U1s. And now there's a key point because non-abelian gauge groups are local, and then you break it, it becomes a local U1. That's different in 16. 60 U1s must be global, but now it can be local. And that means we have more flexibility to build the U1 gauge groups. And in particular, we can build very exotic U1s that can realize much higher charges than before. And this point has been noticed in one of our previous papers. So now in this work, we will focus on a single U1 gauge factor, and which is decoupled from other sectors in the theory. So in our model, there will be many gauge factors, including abelian ones and non-abelian ones. So now we just have one abelian one, and then it will be decoupled with all the other gauge factors. Namely, there's no matter that is charged under both the U1 and the non-abelian sector. So now in this setup, we break the non-abelian gauge group with flux, and then the result is we can achieve the following charges. So if we look at vector light fields, which may get some light masses, then it has Q equals 657, which is 100 times larger than before. And if we look at 3 massless chiral fields, we also can get Q equals 465, which is also a pretty large number. So now let me tell you how do we achieve this result. First of all, let me review some basics of 4D F-theory models. You can think of F-theory as a kind of type 2B compactification on a compact Kähler manifold, but this manifold is not a KBL in general because we are in a strongly coupled setup with a bunch of 7 rings floating around. So that threefold is not KBL in general, and we call that threefold as a base. And then we insert at each point of the base, insert a torus, or we call elliptic curve that represent the axial diatom background. And then the whole thing we require to be KBL. So the whole thing we'll call elliptic KBL fourfold. And now the gauge theory data will be specified by singularities in the elliptic vibration. So for example, for complex codimension 1 singularities, the degrees will tell you what gauge group you have in low energy. That codimension 1 singularities is exactly the Brink stacks that you have in, let's say, 2B string theory. And if we intersect these singularities together to produce more additional codimension 2 singularities, that will tell you what kind of vector representations that you have in your theory. So now, in order to do calculation, we need several notations for the devices, which is an algebraic codimension 1 locus in the internal manifold. So the first of all, we need something called d alpha. D alpha stands for we take a divisor on the base, and then we pull it back to the whole elliptic vibration. And the second one is a di. So we have singularities on some locus, and we need to resolve it by blowing it up. By blowing it up, we get some additional divisors, which we call exceptional Cartan divisors. And it's known that the intersection structure resembles the Dynkin diagram of the gauge group. So the structure of this Cartan divisor exactly tell you what the gauge group you have. And there's a third thing called sigma. Sigma is simply the divisor that supports a given gauge group. And now specifying the geometry, we also need to add flux. So the flux is best understood in the dual M theory picture, where we have a 3-form potential and its derivative is a 4-form flux. And in particular, we would need a type of flux called vertical flux. That vertical flux can be expressed as products between 2 1-1 forms. And those 1-1 forms are also Poincare duals of the divisor. So in general, we can write as G4 vert equals some flux parameter, and then di wedge dj, the product of 1-1 form, and then the flux parameter phi ij, and then we sum it up. And then we also define the integration of this vertical flux to be theta ij. Now, it has been known that the I alpha components of the thetas can break the gauge group. So in our previous paper, we have write down this simple condition for breaking the gauge group. So if this summation of bi theta I alpha, where the inner product of alpha I, the simple roots, so alpha I denotes the simple roots here. So Sorry for repeating the notation for alpha, but I hope you understand that. So if this condition is non-zero for some alpha, then we say that the root bi alpha I in the non-abelian gauge group is broken. And not only that, the corresponding Cartan generators, right, written here, that are also broken. So now you notice that this inner product of alpha I is accounting for the effect from non-ADE gauge groups. In ADE gauge groups, that factor doesn't exist here. But later on, we'll use non-ADE groups to break down to U1, so we can't need to keep that. And there are many other flux constraints we need to satisfy. Let's say, for example, primitivity, the flux need to be primitive. And in order to do that, again, we derive this simple inequality in our previous paper, which is the H11 of the gauge device sigma need to be greater than the change of the rank of the gauge group. And this inequality will play a crucial role in our analysis. So far, we are talking about breaking non-abelian gauge factors to some other non-abelian gauge factors. But how about we break it down to a single U1, and we can actually do that. So we now impose another very similar condition, which I just replace bi by pi, which means those pi's will not along any route. And we set it if equal to 0 for all alphas. That means there will be a single U1 Cartan direction to be preserved, but there's no roots to be preserved. And by carefully tuning the fluxes, we can actually get very exotic U1s, as shown in this figure. So imagine you have two Cartan directions, U11 and U12, and then we can pick the flux such that the preserved U1 is along this change direction. And then you imagine you project the gauge charges before breaking onto this line, and then those will become very exotic numbers. And that is how we get some very large charges from this flux breaking. But on the other hand, this is not arbitrarily exotic. So if we pick a more and more exotic directions of U1, we will require more and more amount of flux by flux quantization in order to satisfy the condition we wrote down. And if you include larger and larger flux, finally you will hit the tadpole bound. And then that means you have an upper bound for the U1 charge that you can have. So let me show you the formalism by this simple example. So let's say we consider SU3 supported on a hexaploid surface F0. And let me remind you that F0 is just a P1 cross P1. And we call each P1 to be S and F with the written with the intersection number given here. So the method before breaking for generic SU3 F3 model, it will be the SU3 fundamental, the anti-fundamental, and the adjoint. Now we notice that H11 of S0 is 2. So according to the previous condition, we can reduce the rank of the gauge group by 1. So we can do, let's say, SU3 down to U1. And then now we impose the condition that we write down before, and we pick some numbers, let's say -2 and 5 here. And then by some group theory calculation, you can calculate the charges you get after the breaking, and then you'll get Q equals 2, 3, 5, 7, 9, and 12. And now you'll notice that there's already a 12 here, which is already larger than the 6 before. So just by this very simple setup, we already get some large charges. But can we do better? We will see. Now let me be more explicit. So now we write down the flux constraints, and then we can solve it. The flux can be expressed in this very simple form where NS and NF are just some integers. Given the flux, we can also calculate the Cal spectrum. Because we are turning on vertical fluxes, it is known that vertical flux will induce Cal matter in the theory. So you can calculate the Cal matter spectrum given by this equation. There is some Cal matter of charge 3, charge 12, and charge -9. And you can check that anomaly is cancelled here. And in fact, in our paper, we proved that no matter which flux you turn on, which direction of U1 you preserve, anomaly will always cancel in this geometry. So now this is the idea of getting large charges. All the remaining we have to do is to optimize the procedure to get largest charge as possible. So how do we do that? So let me remind you that the upper bound of the charge is basically controlled by the tadpole condition, which is the inequality that written here. from here, you can notice two things. First of all, we need to maximize the charges. To maximize the charges, we need to maximize the flux, the amount of flux that we can turn on. So we are maximizing phi. And to maximizing phi, look at this inequality. First of all, the right-hand side, of course, it should be as large as possible. So we need to get a very large order characteristic chi. But on the other hand, on the left-hand side, the integral of G for wedge G4 looks something like phi squared times some intersection numbers in the geometry. So we also need to pick gauge divisor geometry that has a very small intersection numbers. So only when we do both things, we can get sort of the largest charge possible. And now all we have to do is to search in a list of elliptic RBL fourfolds such that we maximize chi and minimize the intersection numbers. And it would be natural to do it in the Cruiser-Scark database or KS database, because it's known that the KS database, although the list is far from complete, it is behaving very good at large chi. But now I need to warn you that by looking at this procedure, you see these solutions with very large charges, they're exponentially rare in the landscape because we are aligning all the flux along one certain direction, and that will require very extreme amounts of fine-tuning. And because now we have used up all the flux to break the gauge group, there's no flux for you to do, let's say, modular stabilization. So these are very weird models in the landscape that, of course, have nothing to do with phenomenology. If we try to look at generic solutions that is potentially relevant to phenomenology, we would expect that they tend to have very small charges. So now, which geometry we are going to pick in the KS database? The funny thing is, we are not picking the largest chi. We are picking something slightly smaller. We are picking the 5th largest chi in the KS database. There are many fourfolds that have the same chi, and to get an easy analysis, we are picking the ones that has the smallest H11 and the largest H31. So now the Hodge number is shown here. And this geometry is known to have many rigid gauge group factors or geometrically non-hexable factors. Those are gauge factors that independent of moduli. So given the geometry, you already automatically get these gauge factors. And we call geometrically non-hexable because they are not really non-hexable. We are going to break it by fluxes. So these are the gauge factors. And another thing is all the gauge divisors that support these gauge factors, again, they have H11 equals to 2. So at most, we can decrease the rank of the gauge group by 1. So now, how do we get a U1 here? You see that the only choice that you can have is a G2, break it down to U1. So now we are forced to consider G2 gauge groups, which is a non-AD groups, as I said before. And after that, we can get a U1 factor that is decoupled from all the other gauge group factors. Now, the reason that we are picking a 5th largest chi is that in that geometry, there exists a G2, which is supported on F0. And that is really good for us because F0, as I showed you before, the intersection numbers are very small. It's just 1 and 0. And let's say if we pick a largest chi in the KS database, we will get something like a G2 supported on the F12, which has a much higher intersection numbers, and that will actually give you a smaller charge. So we notice that we can maximize the charge by pick this the 5th largest chi geometry. And in order to do that, we mentioned that in that setup, the representation of G2 that is present in the theory are simply the G2 fundamental, the 7, and the G2 adjoint, the 14. Now, given this setup, we just do the same thing as before. We impose some general U1 direction that we want to preserve, and then we solve all the flux constraint and maximize one of the charges. So let's say we want to maximize one of the charge in the G2 adjoint listed in here. And then we try to saturate the tadpole bound, and that will give me some candidate numbers for A and B. So let's say if we pick A and B to be 329 and 657, that will almost saturate the tadpole bound, and it will maximize one of the charge in the adjoints to be 657. And that's for me, it's a really surprising result because that number is really, really larger than the previous one, which is Q equals 6, right? And if you calculate the spectrum more carefully, you will notice that that charge is not a chiral field. You calculate the chiral index, it will give you 0, so it's a real vector-like field. So you may argue that vector-like field, okay, it may get some masses from, let's say, the superpotential, and how about we try to get some truly massless field? To get a truly massless field, we need to look at charges that have a non-trivial chiral index. And it turns out in this setup, the 657 cannot be chiral, but you can just slightly modify this model, and then it will give you a 465 as a chiral matter charge. Now, we are focusing on the adjoints only, but we just briefly mentioned that the G2 fundamental will give smaller charges than that. Now, is this really the best that we can do? We believe the answer is yes, but we are not rigorously proven that. We are giving heuristic argument for that. So the first heuristic argument is that in all the examples that we look at, so the first thing is, can we just pick a larger chi and do better? In all the examples that we look at, the answer is no. So Q is usually smaller if we pick a slightly larger chi, but we are just looking at examples. We cannot rigorously prove that, because especially if we look at geometry with much higher H11, the analysis will be much more difficult. And the second question is the K-state base really give us the largest chi? And we, again, believe the answer is yes. So there are various reasons for that. First of all, it has been proven that toric hypersurface KPL, which is exactly what the K-state base is giving, that is largest, some analog of chi in 6D. And it's not unreasonable to believe that maybe the same statement will be true for 4D. And there's also an analogous minimal model program in KPL 4 volts that show that maybe this toric hypersurface, so at least possibly, will give you the largest chi that is available. And the second question is, can I break other gauge group to get U1 charges? There are several points on that. First of all, breaking other gauge groups will require lower chi. So as you see before, if we pick a large chi, the gauge group that is only available is G2. So if we need to look at other choices, we need to lower the chi by quite a bit. So that already decreasing the gauge charge, decreasing the U1 charges. And the second point is, no matter which nonabelian factors you choose at the beginning, we notice that you can just maximize the charges by localizing all the flux on one of the Dynkin nodes, almost. And that means even you add much more Dynkin nodes on the other side in the Dynkin diagram, we believe that that will not affect the results so much. So that means picking another gauge factors, we believe it won't modify the procedure very much. And the third point is G2 itself is a very exotic gauge group. It has the most exotic roots by having a component of 3. That is pretty informal, but G2 also look kind of promising to us. And the final point is this flux breaking is so far the most flexible way of constructing these U1 factors. It's much more flexible than constructing rational sections. It's also much more flexible than the field theory hexing. So unless there is a completely new formalism that comes out in literature, we believe flux breaking is doing the best so far. But on the other hand, so far we are just focusing on a single U1 factor in the theory that is decoupled. So in our paper, we already show that if you couple this U1 to some other nonabelian gauge factors, let's say a E6 factor, then actually you can get slightly larger charges than the 657 that I showed you before. So now let's conclude what we have got. So the main result is very simple. We found new U1 models with much larger charges, Q equals 657, comparing with previous literature. And there are certainly many directions to go on. The first one is this kind of U1 spectrum. It is tightly related to a certain kind of U1 spectrum in 6D that is ruled out by the so-called automatic enhancement conjecture. This tells you that if you have this kind of spectrum in 6D, then you actually get a larger gauge group than you would expect. And once you go back to a larger gauge group, you'll find that these charges are no longer large. And it will be interesting to study. So we now basically already know that it will evade this automatic enhancement conjecture for some reason, but it will be interesting to investigate what the deeper relation between this kind of concepts. And the second thing is we noticed that the flux breaking is really effective for exploring new corners in the string landscape. So are there more applications for that? So in our previous paper, you may already heard of that. We use the same formalism basically to break rigid gauge groups in F-theory down to standard model gauge group. And from that, we can build some really promising standard model-like F-theory models. And that's one of the applications, and are there more? We will continue to investigate that. And the first thing is, so far we are just giving you heuristic argument for why 657 is basically the best we can do, but there are much more work to solidify the statement. And the final thing is, we are working on F-theory, but in principle, you can also do the same for example, type 2B string theory. Of course, in type 2B, you only have perturbative sets up, so the result will be rather limited. But it will still be interesting to compare in different corners of string theory how best we can do. So that is all the future directions that we have in our mind so far. And thank you for listening.
Okay. Thank you very much, Ian. Are there any questions? So maybe can I ask a question about this automatic enhancement aspect of this 4D model? So in what sense is it related? And in what sense are you evading it? The particular G2 example that you wrote.
Oh, yeah. So the automatic enhancement conjecture especially rule out the infinite swarmland of UN charges in 60 that Andrew has been working on. And this UN spectrum that we are getting is actually basically the same as that UN spectrum in 60. But now there are two different things. The first thing is we explicitly have a tactical bound, so it's not really infinite family of them. And the second thing is now we are explicitly breaking the gauge group by fluxes in a supersymmetric way. We solve the permittivity condition to ensure it's still a supersymmetric solution. So we just don't see any way for it to enhance back to non-abelian gauge groups because the obstruction is already there.
Right. Okay. Any other questions? Yes, Marcus.
Yeah, so just to make sure, do you find in any circumstances situations where all the U1 masses have a common divisor? So all charges you find is a multiple of 3 or 4, or do you always find a set of charges which basically are Crow prime such that you can always construct a state of charge 1 essentially?
We just normalize all the charges by hand such that their GCD is 1. So an example would be here we have a 1 and then some 300 numbers and then 657. They are clearly co-prime. In some other examples, there may not be a charge 1, but we can, so because this charge are quantized, so we can always impose that normalization.
Okay, thank you.
Okay. Are there any other questions? If not, then let's thank Shing Yan and also Nicholas again for their excellent talks. And see you